Hello everyone! Today I will present our paper Joint Goal and Strategy Inference across Heterogeneous Demonstrators via Reward Network Distillation. I am Letian Chen. This is a work done in Robotics Lab with my colleagues Rohan Paleja, Muyleng Ghuy, and my advisor Matthew Gombolay. First of all, why do we need to do learn from demonstration? Why don't we just apply standard reinforcement learning algorithms to an MDP and get optimal policy out of it? The biggest problem in the process is the design of reward R is not trivial. Previous study has shown that the designed R may not generate the desired outcome. It may not even be possible for experts to design a reward function despite the fact that they could give demonstrations. To address these problems, inverse reinforcement learning takes expert trajectories as input and outputs the inferred reward function, as well as a policy pi that behaves similar to demonstrators' policy. So what are some fundamental problems IRL have? The first one is heterogeneity, which means different demonstrators achieve the same goal but take different strategies. This will jeopardize typical imitation learning or inverse reinforcement learning methods, as they will receive different labeling signals. The second one is reward ambiguity, which means given an observed behavior, many reward functions could actually explain it. Let me illustrate the two problems using the example of tennis. Here are 4 examples of tennis strikes. They all share the same task, that is to return the ball back to opponent's side, while their swinging strategies are different. If we try to learn a reward function that explains all the demonstrations, we'll suffer from heterogeneity. We could also learn a reward function corresponding to each demonstration. This way, we avoid the heterogeneity of the demonstrations, but will suffer from data inefficiency and reward ambiguity. To be short, heterogeneity rises when we have large amount of data, while ambiguity rises when we have too little data. Is there a way we could utilize all the abundant data while not be hurt by heterogeneity? Here, we propose a framework called multi-strategy reward distillation. In MSRD, we have a shared task reward and specific strategy reward for each strategy. Specifically, all the demonstrations share the task reward part, and thus task reward learning suffers less from reward ambiguity. The strategy reward part is our solution to heterogeneity, by which each strategy demonstration could have its own strategic preferences. Before we dive into the learning method for MSRD, let me first introduce 2 previous work that is foundation of MSRD. The first one is adversarial inverse reinforcement learning, an ARL algorithm. In ARL, we learn a discriminator that tries to discriminate the generated state action pair and the demonstrated state action pair. Specifically in ARL, discriminator is directly given by reward function, which is parameterized by theta. Using the reward function learned in discriminator, we could train a policy maximizing the reward, which gives us the generated state action pair. We could iterate between the 2 processes and finally converge the reward function to the reward function demonstrator is optimizing and the policy that behaves similar to demonstrator. The second previous work is distillation. Distillation is a knowledge transfer method. It works by distilling peripheral neural networks knowledge into center neural network and then train each peripheral neural network with the actual goal while being regularized by the center network. By iterating over the 2 processes, center network learns the shared knowledge between tasks, and knowledge distilled by center network also flow to each peripheral network. In MSRD, we change policy distillation to be reward distillation, and we maximize jointly an AAR objective, which means peripheral reward learning from demonstration, and a regularization objective, which transfer each strategy reward to the task reward and regularize each reward to be close to the task reward. However, such learning will progress slowly because R theta 0 will work as a strong regularization for R theta I before successful distillation, since we initialize R theta 0 to be 0. How can we make this better? we propose reparameterization, in which we parameterize the reward that demonstrations are optimizing as a linear combination of the task reward and the strategic specific rewards. By such reparameterization, the reward is now both parameterized by theta I and theta 0. And thus, ARL objective will directly update theta 0 instead of waiting for the knowledge to be learned by theta I. In the meantime, regularization becomes a simple L2 regularization on strategy-only rewards. This also provides us an intuition to explain MSRD. Optimizing only via IRL objective leads to recovery of a combination of task and strategy rewards. And adding the regularization on strategy reward encourages to encode the theta I only necessary information and share as much as possible knowledge in theta 0. Let me summarize our algorithmic model. We first have a reward function that is parameterized by task network and a strategy network. We could train RL on such a reward, get a policy, and collect a rollout dataset. Put together with an expert dataset, we could randomly draw a state action pair to train discriminator, which in ARL is also the reward function. We could do such operations for all the strategies and share a single task network. To show the effectiveness of MSRD, we tested for two hypotheses. The first one is that MSRD recovers better task reward than ARL. To test this hypothesis, we first generate the strategies via DIN and KLSAC. We show that MSRD's task reward has higher correlation with ground truth reward than ARL when evaluated on collected trajectories. The second hypothesis we tested is that MSRD recovers better strategy reward than ARL. Since it is in simulation, we know the ground truth strategic preferences. We show that MSRD's strategy reward has a significantly better correlation than ARL's reward function. We also showed this qualitatively. In the cart pole domain, the task is to keep the pole upright, which is exactly recovered by the task reward, which has its peak when pendulum angle equal to 0. In strategy 4, demonstration keeps the pole a little right, but still stable, which is precisely recovered by strategy 4's strategy reward, which has its peak on a little positive pendulum angle. Strategy 13 has opposite preferences and encourages the pole to tilt left. We also tested MSRD on a real robot table tennis domain, in which we have 3 strategies. The first one is push. The second one is slice. And the third one is top spin. With only 30 minutes of training and 3 demonstrations on each strategy, the robot was able to hit 83% of the serves and successfully return 90% by topspin. A natural question to ask is that what did task reward learn in this domain? We could expect it to learn whether the ball is returned successfully. To show that, we compared the task reward for successful trajectories and virtually manipulated unsuccessful trajectories, and found that task reward for successful trajectories is significantly higher. We also investigated what the strategy rewards had learned. To show that, we evaluated each strategy reward on each strategy trajectories, and found that push strategy reward give highest reward to corresponding push trajectory, so a slice reward and top spin. In conclusion, MSRD is a framework in which we could jointly infer task reward and strategy reward. By teasing out the style or strategy from heterogeneous demonstrators, we achieve better task reward, which means better understanding of the task, and better strategy reward, which means better understanding of demonstrators' own preferences. Thank you.